Let's look now at some better ways to remember how to compute the tangential and normal components of acceleration. So the tangential component, if you remember from the last video, is nu prime of t. In other words, this is d dt of the magnitude of r prime of t. All right? Well, the derivative of the magnitude here, this is just going to be r prime of t dot product r double prime of t over the magnitude of r prime of t. Right, remember the magnitude of a vector is the square root of the dot product of the vector with itself. So using the chain rule followed by the product rule, we can get this. Right? Or I guess we can say using a product rule inside of a chain rule. Okay. Well, we can interpret that in terms of velocity and acceleration as well. This would be the velocity dot product with the acceleration divided by, well, here's the magnitude of velocity, so that's just nu of t, the speed. So this formula right here will give it purely in terms of r, but this one here gives it sort of a more physical meaning. Okay, let's also think about the normal component of acceleration. Remember, this was the speed quantity squared times the curvature. Well, okay, so again, the speed here is, sorry, the speed is the magnitude of r prime of t, right? And we're squaring this. And remember that the curvature is given as the magnitude of r prime of t cross r double prime of t over the magnitude of r prime of t cubed. Right? So let's combine that all together in one equation, and that will tell us that the normal component of the acceleration is magnitude r prime of t cross r double prime of t. And this is going to end up, in the end, just divided by one factor of r prime, magnitude r prime of t. And again, we can put the physical meanings in here again. So this would be the magnitude of velocity cross product with acceleration divided by the speed. Okay? So remember, one of the reasons we did this was so that we could write the acceleration vector as at of t plus an, sorry, not at of t, at times t, and an times n. All right? But let's remember some properties of t and n real quick. Remember that they're orthonormal to each other, which means that t dot t and n dot n are both equal to 1, right? They both have magnitude 1, the unit tangent and unit normal. So that means the dot product of them with themselves is 1. But it also means one more thing. It means that t dot n is 0. That's the normal part of it, right? So the ortho, or sorry, that's the normal part of it. The ortho part is dot product equals 0. The normal part is the dot products equal 1. All right, so where does that get us? Well, what that conveniently tells us is that A, the acceleration vector, dot product with t, well, that's just at. And what it also tells us is that A dot product n is just an. Okay, so that could be useful as well, right? But there's one more interesting fact here that we have. So we've taken the dot product of A with t and with n. Let's do the dot product of A with itself now. Because A, remember, is written in terms of t and A. All right? So let's do this. A dot product A, well, what is that? That's just the magnitude of A squared. That's one way to interpret it. But now let's actually write it as the dot product of this thing here with itself. So this will be AT times T plus AN times N, dot product with that same thing. AT times T plus AN times N. All right. And, well, if we're taking the dot product of the sum of two things, this is just like like foiling something out, basically. So we'll have this dot product with this first term here. Well, what does that give us? We have the two ATs, so AT squared, and then we have T dot T, but that's just 1, so we can leave that off, right? And then we have AT T dot product with AN. Well, so we have AT times AN, but then we have T dot product N. And that's 0 from over there. So we can leave that off here. So let's move on to the next one now. AN times N dot product AT times T. Well, that's really just the same thing, so that's also 0. And finally, we have ANN dot product ANN. Well, so it gives us AN squared, and then N dot product N is just 1, so we're done here. So what has happened? We've written the magnitude of acceleration squared as AT squared plus AN squared. In other words, the magnitude of the acceleration, this is just the square root of AT squared plus AN squared. Right? So that's a neat little trick that comes along with having these normal and tangential components of acceleration. It gives us all different ways to get at them.